Hi, I'm Arianna Punzalan. I'm a student in the graduate degree program in ecology at Colorado State University, and this is my public defense seminar. I wanted to make it available so that my family, friends, and colleagues could see what I've been working on for my master's degree, and I hope you enjoy it. Predicting Condor Range Expansion in California to reduce development threats. As the human population grows, human-wildlife conflicts have become increasingly frequent. Among those conflicts are strike risks that wind turbines pose to bird and bat species. In the United States, bird mortality rates from wind turbines are estimated to be in the hundreds of thousands every year, and these mortality rates are expected to increase, especially as the U.S. transitions to more renewable energy sources. The United States hopes to have 20% of its total energy generated from wind power by 2030, and many states are taking initiatives to harvest more renewable energy as well. California currently produces about a quarter of its energy from renewable sources, and the Clean Energy and Pollution Reduction Act of 2015 requires that this percentage increase to 50% by the end of 2030, suggesting that more wind energy farms are to be constructed. The collision risk with wind turbines is not equal across all bird species. Those that deploy migratory strategies use habitats that generate high wind potential, and those that have moderate dispersal rates all result in significantly higher collisions with wind turbines. And large soaring birds, such as raptors, storks, and vultures, also have high risk and rates of collision with the turbines due to their usage of wind generated from mountainsides, high wing loading, and low maneuverability. Collisions with wind turbines can have even greater consequences for species that can't offset losses of individuals due to their small population size and low reproductive rates. One such species is the critically endangered California condor. So just a little bit of background about the California condor. They are the largest flying land bird of North America, and they have a 9.5-foot wingspan, which they use to soar large distances looking for food. Condors are vultures, so they're obligate scavengers, meaning they only eat what is already dead, and in that way, they're nature's cleanup crew and they help reduce the spread of disease. Condors are social, which is an adaptation in many vulture species that aids in exchanging information and finding food that only exists temporarily in space and time. Condors are also monogamous for the most part. Like other monogamous species, things can happen. There can be extramarital affairs, per se, and condors can break up. And unfortunately, sometimes a mate will pass away, leaving the surviving condor mateless and in search of a new partner. Condors are long-lived and they have a delayed sexual maturity. It's thought that condors can live up to 60 to 70 years of age. Condor number 1 of the Condor program is named Topa Topa. He's 54 and still actively breeding. But unfortunately, in the wild, condors tend to die before they reach old age. And this contributes to the reason why, like the majority of vulture species worldwide, condors are endangered. And condors are actually critically endangered. The main threat to condor survival today is lead poisoning. Like I said, condors are obligate scavengers and only eat animals that have already died. And sometimes those animals have been shot with lead, and sometimes those animals have been shot with lead bullets. So condors will unknowingly ingest small pieces of lead, which is a toxic substance, and oftentimes proves to be fatal. But while lead poisoning is the main threat to condor survival today, a multitude of pressures led to the historic decline of the species, and by 1982, the population had plummeted to just 22 individuals in the wild, which sparked an effort to save the species and capture all remaining condor birds in the wild and bring them into captivity for a captive breeding program. And since 1992, condors have been released into the wild out of different release sites in California, Baja California, and Arizona. And within California, there are 2 seemingly distinct flocks. There's one in Central California, co-managed by Pinnacles National Park and Ventana Wildlife Society, and one in Southern California that's managed by the U.S. Fish and Wildlife Service. So thanks to the intensive monitoring and management of condors by the Condor Recovery Program, There are now just over 300 condors in the wild. And this increased population is considered a success from the recovery standpoint, but it also comes with management challenges and increased exposure to threats. A survival analysis published in 2017 found that as condor flocks increase in age and size, condors are increasingly likely to range more widely, and they're more likely to go undetected from monitoring methods, and they're less likely to be observed feeding on proffered food. These wilder behaviors are associated with lower survival. Challenges that come with increased population size include decreased monitoring success. So all condors in the wild have radio tags and are tracked using a combination of methods. But as condors increase their range size and move into areas that are more difficult to access, such as private property or remote areas, it becomes more challenging for agencies to conduct survival and mortality monitoring. There's also a concern that as condors range more widely and feed less on proffered food, there's an increased likelihood of condors being exposed to lead in the food that they eat, especially as they use areas beyond where managing agencies concentrate non-lead outreach and education. There is also a growing concern of conflict with wind turbines. So development within current documented condor range requires consultation and planning with the U.S. Fish and Wildlife Service during environmental impact assessments. However, most wind energy developers think condor flocks only exist within their current ranges and don't consider possible range expansion when proposing new projects. And this may result in development within condor habitat that is currently unoccupied, but is likely to become inhabited over the duration of a wind farm's lifetime, which is decades long. And this development can be really harmful to condor recovery. So this concern led me to ask one main question that drove this study, which is, where is there likely to be conflict between condor range expansion and wind energy development? And to answer this question, I needed to ask a few more questions. So first, what do condor home ranges look like, and are they growing? Second, what factors influence condor home range area? Where will condors likely expand their range, and will the two flocks in California merge? And then finally, circle back to, where is there likely to be conflict between condor range expansion and wind energy development? Luckily, these 4 questions translated really well into a 4-step process, which I followed for this project. So step 1, estimate the core areas and home range areas of condors. Step 2, identify factors that influence home range area through a statistical analysis. Step 3, create a tool that will predict where condors are likely to expand their range. And then step 4, do a GIS analysis to identify where that predicted range overlaps with commercially valuable wind. So my first chapter, titled Factors Influencing Annual Home Range Size of California Condors, focused on steps 1 and 2. So animals typically have spatial boundaries that encompass their movements as they search for food, mates, and shelter. And these spatial boundaries in which animals typically spend their time are called a home range. Home ranges are likely to change based on information gathered through experience. So examining home ranges really helps to understand the relationship between animals and their environment. Core areas are regions within home ranges that are used more extensively than expected under a uniform distribution of use. So core areas are really just hotspots of activity within a home range. My study area included Central and Southern California. In Central California, condors typically range west along the Big Sur coastline from Monterey to San Luis Obispo County, and also inland throughout San Benito County and parts of western Fresno County. In Southern California, condors typically range throughout the Los Padres National Forest in Santa Barbara and Ventura counties, and then up into the Tehachapi Mountains in Kern County. Condors use a variety of habitats ranging from rocky outcroppings to redwood forests and grazing pastures on both public and private property. I used location data collected by GPS units placed on condors between 2006 and 2017, and I cleaned all of the data of any locations that had diagnostic errors. And since the data was collected at different sampling schedules, I subset the data to one location fix per hour, and I only kept records that had at least 6 months of cumulative data to represent an annual home range. I estimated core and home range areas using the CTMM Shiny app, which is a graphic user interface for the continuous time movement modeling package for R. And this allowed me to quantify home ranges with kernel density estimations that take into account both spatial and temporal autocorrelation. So the idea that data that is collected closer together in space or time are more similar than those that are collected further apart from each other, thus are not independent and identically distributed. I ended up with 375 annual core areas and home range areas for 123 condors wearing GPS units throughout my study period. And I used 50% volume contours and 95% volume contours to represent core areas and home ranges. So there is a 50% chance of finding a condor within their core area at any given point in time, and then you have a 95% chance of finding a condor within their home range at any given point in time. And this is a map of just examples of what those core areas and home ranges look like for 3 different condors during the year 2017. Once I had estimated the core areas and home ranges of condors, I needed to identify factors that are associated with home range size. I considered a total of 21 different variables related to condor biology, management, and habitat requirements, and I split those variables into 8 different categories. Because condors are so highly managed and monitored, all of the individual management and population information was already known. And then I used environmental variables and surfaces that were previously generated and assessed for a habitat suitability model. And I used these same environmental variables because factors that are used to predict habitat suitability for condors also likely influence their home range size. I used the zonal statistics tool in ArcGIS to calculate the mean or majority values of the environmental variables for each home range. I then conducted a stepwise model selection to identify which variables are associated with home range area. And I used linear mixed effects models and included Condor ID as a random effect to account for correlations induced by repeated sampling. So some condors had more than one home range estimated over the study period, and so I wanted to take into account correlations between those home ranges. My response variable was home range area in kilometers squared, and I estimated all of the linear mixed models using maximum likelihood to compare models with different fixed variables using Akaike's information criterion. I found that the top model that best explained home range size included age group, time spent in the wild, age or experience of managing agency, slope, NDVI, distance to water, and road density. The life stage of condors affects their home range size. Condors in different age groups have different fitness priorities, which is reflected in the average home range sizes of each age group. I found that subadults have the largest home ranges on average, and this is because they are seeking to improve chances of survival by exploring the landscape looking for the best resources. I found that breeding adults, on the other hand, have the smallest home ranges on average, and this is because they're focusing on reproduction and limiting their movements to areas around their nests, which are typically in established territories. Additionally, as condors spend more time in the wild and gain information about the landscape and settle into territories, their home ranges shrink. Social attraction may also influence home range size. When condors were first reintroduced to the wild, they were released without any knowledge of the landscape or other condors to learn from. But as bolder individuals discovered more feeding, roosting, and nesting habitats farther away from release sites, less knowledgeable condors could follow them, and each year more area became known to the condor population, which helps to explain why home ranges increase as managing agencies gain years of experience releasing and managing condors. Resource availability also affects home range area, and generally, home ranges will be smaller where there are better resources. I found that as slope increased, home range areas decrease. I included slope as a proxy for cliffs, which condors use for nesting, roosting, and thermal updrafts. So it makes sense that where there are more cliffs, the home range sizes decrease. I also found that as NDVI increases, home range area also increases. I included NDVI as a proxy for prey availability because vegetation productivity is strongly correlated with the abundance of deer and elk in California. However, home ranges increase as vegetation productivity increases, suggesting while there are more deer or elk available, there are likely fewer animals that are dying for condors to feed on because condors are vultures. So it's more likely that prey mortality is a better attractor for condors, and this is seen in Ruppel's vultures and lappet-based vultures that cluster around migratory herds during the dry season when more ungulates perish. I also found that as distance to fresh water increased, home range area decreased. And this result was surprising because condors do like fresh water for bathing, but there are water troughs and artificial ponds in grazing lands that condors can use, which were not included in this study, so that effect may have been missed. However, it also could be that there is more prey mortality in areas farther away from freshwater sources, which creates more feeding opportunities for condors, thus would decrease their home range area and support that finding. Finally, I found that as road density increases, home range area also increases. Condors are sensitive to human disturbance, and they're less likely to nest in areas with greater access to humans, and they also prefer undisturbed and undeveloped areas that support grazing. I thought that maybe an increase in road density could create more feeding opportunities due to higher roadkill. However, other vulture species prefer foraging on carrion away from roads, suggesting a trade-off between energy intake and safety. So areas with more roads may be perceived as dangerous, and condors may be willing to traverse more land to find food in safer areas. So in summary, in this chapter, I found that life stage, social attraction, and resources all affect condor home range sizes. So I've now estimated the core and home range areas of condors through years 2006 and 2017, and I have identified the factors that influence their home range areas. Now I need to focus on predicting where condors are likely to expand their range and identify where these predicted ranges overlap with commercially valuable wind. And that's what I focus on in my second chapter, very creatively named Range Expansion of California Condors and Overlap with Commercially Valuable Wind. So I know what condor home ranges look like and what influences their home range sizes. I also happen to know where there is suitable habitat for condors to occupy. So I put this information together in a tool to predict where condors are likely to expand their range. And this habitat suitability surface also serves as my study area. So areas that have lighter colors are more suitable for condor occupation than darker colors. So the overarching goal of this predictive tool was to create something in which a user can customize the population demographics of the two condor flocks in California and predict the overlapping home ranges of those populations, to then consider how those home ranges may be affected by wind energy development. I used NetLogo, which is a software used for agent-based model, and my tool differs from standard agent-based models because the individuals in my model are programmed to execute tasks, but they don't interact, learn, or adapt. So an overview, just to give a brief overview of this tool, it consisted of two models. And the first model wasn't meant for general use, but it created input that was necessary for this, that's needed for the second model. And this input was a list of potential roost sites from which home ranges could grow. And these potential roost sites were generated from the combined core areas observed in 2017. And I also use this tool to set the rules by which home ranges grow into suitable habitat. And these information was exported and used in the second model, which then calculates and maps home ranges. So the second model is the model that estimates and maps condor home ranges into suitable habitat. So a user can determine how many condors in each age group in both the central and southern California flocks to estimate home ranges for, as well as how many years have passed since 1992 when the program began releasing condors. And this slider, this time slider, is used to calculate how much time a condor has spent in the wild based on its age group and also the age of its managing agency. When the user presses go, condors of each age group are generated and assigned a numerical identifier that is matched with a potential roost site that has the same identifier. Each roost site has environmental variables assigned to it, and together with the condor attributes, home range areas were calculated for every condor using the top model identified in Chapter 1. The home ranges are then mapped within the suitable condor habitat in California. And then the user can save these overlapping ranges as an ASCII file for import into a GIS for further analyses. To evaluate how well the tool predicted home ranges, I compared the observed and predicted combined home ranges for the final 2 years included in my study and then 2 years after my study. So years 2016 through 2019. I used the map comparison kit to calculate the fuzzy kappa statistic, which essentially summarizes how similar categorical maps are based on the cell type and location. So using these two map comparisons to illustrate how K-fuzzy works, we can agree that the maps from this first comparison are more similar than the two maps in the bottom comparison. However, using the kappa statistic, we get the same score, but since K-fuzzy incorporates a distance decay function, the top comparison has a better score than the bottom. I found that comparisons of the observed and predicted overlapping home ranges for condor populations during 2016 through 2019 show that my tool works rather well. My lowest K-fuzzy score was for the comparisons in 2019 when a subadult from Central California had an extremely large home range size. But by removing this outlier, I was able to improve the K-fuzzy score to 0.9. So I had high confidence in the predictive ability of this tool. So I then predicted Condor Range Expansion in California under 4 different scenarios for the year 2030. The first scenario predicted condor ranges with the same population demographics of 2019, and I predicted this to see how the overall range would change through time even with the same population. The second scenario I predicted had 150 individuals in each flock with 15 breeding pairs each. And then I predicted 2 scenarios to see how extreme amounts of individuals with the largest and smallest home range areas on average would affect the overall condor range area. So the third scenario, I had 150 individuals each with a majority of breeding adults and a minority of subadults. And then the fourth scenario had the opposite. So 150 individuals per flock with a majority of subadults and a minority of breeders. After I had predicted condor ranges under those four scenarios, I did a GIS analysis to calculate the overlapping area between the predicted condor ranges and high-class winds that are preferred for wind energy development. So those are winds with a class 3 or greater, or speeds that are greater than 6.4 meters per second. And what I found was that there's not much difference between the condor ranges under the four scenarios that I predicted. So just using one of those scenarios as an example here. In all four scenarios, the Central and Southern California ranges didn't overlap. There was some meeting of the ranges, but that only indicates that at some point in time, condors from the two flocks used the same area. I also found that less than 10% of the predicted condor range overlapped with high-class winds, and more than 81% of high-class winds were unaffected by condor range. So overall, this tool seems really useful for managers to use to help identify areas in which to concentrate monitoring and outreach efforts. It also seems really useful for managers working with developers during siting and planning stages to reduce the likelihood of conflict between condor ranges and wind energy development. Thoughtfully selecting sites for development is really important in all areas of overlap between predicted condor ranges and commercially valuable wind should be considered during siting and planning stages to reduce any potential negative effects to condor survival. And this is especially important because wind curtailment efforts have been shown to be ineffective in reducing mortality in birds. Thoughtfully selecting sites for development is also really important because a study published in 2018 found that condors in Southern California regularly flew near areas with high-class winds, and 39% of the time that they were flying near those high-class winds, they flew at heights that would place them within the rotor swept zone of wind turbines if those areas were developed. And the development of wind farms in areas where condors are likely to use in the future would place an additional stressor on the survival of a critically endangered species that's already threatened by lead poisoning. Fortunately, there does appear to be many alternative areas where developers can construct turbines that are less likely to impact condor survival and recovery, especially if they're placed a certain distance away from ridgelines with strong orographic updrafts. So for studies in the future, it could be beneficial to create a more complex model that includes exploratory movements, additions of new release sites, and core areas that can also grow through time. Large exploratory movements usually weren't included in a condor's 95% home range area, thus were not included in this project. But those movements could be the most dangerous for those making it because they're usually made by subadult and juveniles that are still learning about the landscape and haven't had the chance to contribute to the condor population yet. Including an option to simulate the new release sites could also be helpful for managing agencies to plan management strategies, especially knowing that the addition of new release sites has the ability to change condor movements because condors are so social. Having core areas that can also grow through time may depict more accurate predictions of Condor Range expansion farther into the future. The potential roost sites from which home ranges grew in my model are constrained to the combined core areas observed in 2017, which predicted Condor ranges fairly well for the scenarios within the near future, but may predict conservative ranges farther into the future. Core areas also reflect the regions within Condor home ranges that are used more heavily than other areas. Therefore, understanding when overlapping core areas would predicting when core areas would overlap would better illustrate true interaction and merging of the two flocks in California. So in summary, my research aimed to answer 4 questions. What do condor home ranges look like, and are they growing? And I estimated the core areas and home range areas of condors through 2006 through 2017 and found that yes, they are growing through time. I wanted to know what influences condor home range area, and I found that life stage, social attraction, and resource availability affects their home ranges. I wanted to know where will condors likely expand their range, and will the two flocks in California merge? I created a tool that helped predict their range expansion, and I found that in all 4 scenarios that I simulated, the two flocks did not merge. And then finally, I wanted to know where is there likely to be conflict between condor range expansion and wind energy development. And I found that less than 10% of every scenario that I predicted ranges for were overlapped with high winds, and more than 81% of commercially valuable wind was unaffected by those predicted ranges. And so with that, I want to thank my advisor, Rainey Boone, and my committee, Cam Aldridge, Lee Zobry, and Jason Ransom. I want to thank the California Condor Recovery Program, particularly the Fish and Wildlife Service, Ventana Wildlife Society, and Pinnacles National Park for all of your data and trusting me with this project. I want to thank everyone who has or still works with the Pinnacles Condor Recovery Program. You guys did a lot to foster my love for endangered species management and natural resource stewardship, and helped me become the researcher I am today. I want to thank the National Park Service, Western National Parks Association, the Ecology Program, and Department of Ecosystem Science and Sustainability for funding and assistantships that helped me do this project. I want to thank Jesse Delia with the USGS for collaborating with me and providing me data that I used for this project as well. I want to thank my writing group, Kara, Tomas, Megan, Sarah, Rena, and Bethy. You guys really supported me and gave me encouragement throughout this last year, and I really want to thank you guys for that. And then finally, I want to thank my friends and family here in Colorado and back home in California. Thank you guys so much for everything that you do. Thank you to my parents for being examples of what hard work looks like. I can't express everything that I'm grateful for in this video, but thank you guys so much. And finally, if you have any questions, please feel free to give me an email, punzalan@colostate.edu. I want to dedicate this to the birds.